Hello students, this lesson is part one of a three-part series on the mathematical idea known as a limit. Now one major objective in Calculus 1 is to develop the tools for determining the rate of change of a function at one particular moment. This amounts to finding the slope of the line tangent to the graph at this moment, which is called a tangent line. Consider the function below. So we have a function here defined as f of x equals negative 1/2 x squared plus 4x, which produces the graph of an upside-down parabola. The x-axis represents time, measured in seconds, and the vertical axis represents the vertical position of some object measured in feet. At time 0, the height is 0. At time 4, the height is a maximum of 8 feet, and at time 8 seconds, the height of the object is back down to 0. Now, slope in general is represented by the letter m, and it is found by doing the change in y-coordinates divided by the change in x-coordinates. Well, the y-coordinates are measured in feet and the x-coordinates are measured in seconds, so the unit of a slope would be a feet per second, which is a rate of change. Now, to pick an arbitrary point right here, coordinates are 2, 6, meaning that 2 seconds into this scenario, the object would have a height of 6 feet. The 6 can be confirmed as the output by plugging 2 into this function and calculating. We get negative 1/2 of 2 squared, which is 4, plus 4 times 2, which is 8. Negative 1/2 of 4 is negative 2 plus 8, and we confirm we get 6. This line here is called a tangent line at x equals 2. It's a line that passes through the point 26 and whose slope indicates the slope of the curve at that moment. And this question, what is the rate of change of this line, in other words, what is the slope of this line, is one major objective of Calculus 1. Now, ordinarily, we would need 2 points to find the slope of a line, but this tangent line is only going through 1 point with any certainty. So as a preview of what we're going to do later in this course, is we're going to pick a second point on the curve, draw the line that connects these 2 points, and then we're going to imagine that red point getting closer and closer to the black point. And as the red dot gets closer to the black dot, we will see that the red line will evolve into the black dotted line. Summarizing, as the red point approaches the black point, the red line approaches the tangent line. Now, underlying all of this will be this notion of a limit. We'll spend the next 3 topics discussing limits, and then return to this context and apply what we have learned. Let's go to the next page. So this is an introduction to the mathematical definition of a limit. Consider the functions below. In this first case, we have a vertical line at x equals a, and some sort of function on the left side of this line. As you imagine a point on this curve getting closer and closer to this x-coordinate x equals a, the outputs of the function appear to be approaching a certain height. Let's call this height L. Now notice this point is hollow, meaning that there is no point actually there. But if that point were there, it would have coordinates a, L. This value L is known as the left-sided limit of this function as x approaches a, from the left. The notation is we have LIM for limit. Below that we write x approaching a, and we put this little minus sign as an exponent on a to indicate that we're approaching a from below a, from the left of a, or from values of a that are less than a. And then we indicate the function that we are analyzing next to this. So we see the value of this limit is L. Another notation is to say, as x approaches a from the left, then the function approaches L, meaning the outputs of the function are approaching an output of L. Now, it did not matter whether this point here is hollow or solid. The point does not need to be there for us to say that the limit is L. In fact, the point could be somewhere else entirely. For example, we could put a solid point right there. This would still be a function of x because it passes the vertical line test. No vertical line intersects the function more than once at a time. And even if I put the point down there below the height L, we would still say that the limit is L, because as x approaches a, the outputs are approaching this height of L. Again, reiterating the language, when you see this symbol, you would say the limit of the function f as x approaches a from the left, or in other words, from below. And again, this represents the single finite value, if it exists, that the outputs are approaching as the inputs approach a from below. This value does not need to match f of a. For example, when I put the dot down below, then f of a would represent that output. And in this case, L and f of a are not the same height. In this middle case, we have the function to the right of x equals a, and we consider what's called a right-sided limit. So when you see this notation LIM, that stands for limit, x approaches a, then you put this plus sign as an exponent on a to indicate we're approaching a from above a, or from the right of a. and next to that we put down the function that we are considering. When you see this notation, you should read out loud the limit of the function f as x approaches a from the right, or you can say from above. And again, this is the single finite value, if it exists, that the outputs are approaching as the inputs approach a from above. This value does not need to match f of a. So in our visual, you imagine a point on this curve that's to the right of x equals a, and then as x gets closer and closer to a from above, this point approaches a certain height. That height is where that hollow point would be. We'll call this L for the limit. This value L does not need to match the output of the function when x actually is a. Currently, I do not see any point on this vertical line, but we could put one. You could put it below L, you could put it at L, or you could put it above L somewhere, or you could just leave it off entirely, and we still say that this function has a right-sided limit of L as x approaches a from above. If there was a point up here, then f of a would be some value that's greater than L. So given how I've labeled this picture, the limit of f of x as x approaches a from above would be equal to L. We can also say as x approaches a from above, then f of x, or you can even say y, if you interpret y as the output coordinate, will approach L. Now in this third scenario, we have the function existing on both sides of the vertical line x equals a, and we address what's called a two-sided limit. The notation is LIM for limit. You do x approaching a, but do not put a minus sign or plus sign as a superscript, and then you write the function next to it. When you see this notation, you should read the limit of the function f as x approaches a from both sides. Now, if both one-sided limits exist and are equal, then the two-sided limit is this single finite value, which is the value that the outputs are approaching as the inputs approach a from both sides. Otherwise, the two-sided limit does not exist, and we use DNE for does not exist. So in this drawing, as x approaches a from below, the outputs of the function approach a certain height. As x approaches a from above, the outputs of the function approach the same height. It's as if they're trying to meet at the exact same height. We use L to represent that height, and so we would say that the two-sided limit exists and would be equal to L. And again, it does not matter what the value of the function actually is when x is a. In other words, look along the vertical line and look to where the solid point is if there is any. So if I put a point below, then f of a would be lower than L, but L would still be the limit. Or I could put the solid point right there, and we would still say L is the limit as well as the output. Or you could put the output up higher than L, but L would still be the limit as x approaches a from both sides. If there is a point somewhere on this vertical line, its coordinates would be a, f of a. An alternate way of writing this, you would simply say, as x approaches a, and then leave off the plus or the minus, so this implies from both sides, then the function, or the y-coordinate, approaches L. Okay, let's put these notions to the test on the next page. Consider the image of the function f below. Find each indicated expression. The first one to consider is the limit of f of x as x approaches -3 from the left. So let's track down where -3 is. This bold horizontal line we'll presume is the x-axis, and this bold vertical line we'll presume is the y-axis. So x equals -3 would be at this location 3 units left of the y-axis. And when finding this first limit as x approaches -3, all that matters is this small window of the graph. As we imagine a point on the curve left of the vertical line, and we get closer and closer to that vertical line, what output coordinate are we approaching? Well, that output is 1, 2, 3, 4 units above the x-axis, which is an output value of 4. So the limit of this function as x approaches -3 from the left would be that output of 4. Next, let's consider the limit of the same function as x approaches -3 but from the right. So go to the right of our orange vertical line. Imagine a point on the curve. As we follow the curve and get closer and closer to the vertical line but from the right side, the outputs are getting closer and closer to this same height of 4. So our limit as x approaches -3 from the right is also 4. So now we consider the limit as x approaches -3. Notice there's no negative or positive exponent, so this means approaching -3 from both sides. And if the two one-sided limits both exist, meaning that there's a numerical value that you can assign to them, and they're equal, then the two-sided limit will be this same value, so also 4. And this final entry in this first column is what is f of -3? To answer this using this visual, you look to the actual output value when the input value is -3, which would be indicated by this solid point, which has a different height than 4. In fact, it's 1 unit below the x-axis, so it would be a height of -1. The coordinates of this point are -3, -1. So this function outputs -1 when the input is -3. Again, this is a good example of where the value of the limit and the value of the output are not the same. The outputs of the function are approaching the output 4 as x gets closer to -3, but when x actually is -3, the output instantly jumps down to -1. Okay, now let's consider the limit as x approaches 0 from the left. So we move our focus to x equals 0, which is the y-axis, and we're only interested in what's going on right here. Now from the left, the outputs are getting closer and closer to a height of 3, but from the right, the outputs are getting closer and closer to a height of 2. So our limit from the left is 3, but our limit from the right is 2. Because these limits are not equal, we say that the two-sided limit does not exist. And then f of 0 is what actually is the output of the function when x is 0. And you can see a solid point right here. That solid point has coordinates 0, 3. 3 is the output of the function when the input is 0. This output of 3 happens to match one of my limits, but that does not need to be the case. Next, let's focus on limits as x approaches 3. X equals 3 is this vertical orange line. Imagine a point on the curve left of the orange line, and as we try to get closer and closer to the orange line, the outputs of this function go up forever without bound, because there's a vertical asymptote occurring here. So you would say that as x approaches 3 from the left, the outputs approach, in this case, positive infinity. Infinity is not a finite number, and so we technically say that this limit does not exist. We say it does not exist because there is no single finite y-coordinate that the outputs of this function are approaching as x approaches 3 from the left. Now from the right, imagine a point on the curve to the right of the orange line, and then follow the function towards the orange line, but from the right, and we can see that we are approaching a height or an output of -2. So we would say that the limit as x approaches 3 from the right is -2. Now again, because these one-sided limits are not equal to each other, we simply say that the two-sided limit does not exist. And then the final question in this column is, what is f of 3? We look to that orange vertical line and look for a solid point somewhere along it, and in this case we do not find one, at least not in the viewing window that we have here. If a function has no solid point along a vertical line, then we would say its output does not exist. So f of 3 has no value. Now let's focus on limits as x approaches 7. So shift our focus to x coordinate 7, and all that matters is what's going on in this little window right here. As x approaches 7 from the left, the outputs of the function are getting closer and closer to a height of 1. It's also true as we approach x equals 7 from the right. In fact, there is a solid point right here whose coordinates are 7, 1. So in this case, the outputs are approaching 1 as the inputs approach 7 from the left. The outputs are also approaching 1 as the inputs approach 7 from the right. Because these are both finite and they are the same number, then the two-sided limit is also 1. And furthermore, that's where the solid dot was implied. So the output is also 1. This is a case where all four numbers are the same. I'm going to take this opportunity to introduce two other kinds of limits that we'll discuss later in this course. Here we have a limit as x approaches -infinity. This is suggesting that as x gets larger and larger, but in the negative sense, is there a single y-coordinate that the graph of the function is approaching? Imagining a point on this graph, and as x gets more and more negative, what are the outputs doing? Well, this function appears to have a horizontal asymptote, whose equation is y equals 1. So as you imagine points on this curve, as the x-coordinates of the points approach -infinity, the outputs of the points appear to be getting closer to an output of 1. So we say the limit as x approaches -infinity of f of x is 1 in this case. And now let's consider a limit as x approaches positive infinity of the function. So we focus on this rightmost piece, imagine a point on the curve, and as we go further and further to the right, ask yourself what are the y-coordinates or the outputs doing? And assuming this behavior here continues, it appears that the outputs are getting closer to -infinity as the x-coordinates approach positive infinity. So we say that the limit here is -infinity, which is a version of does not exist. Now these two limits are known as limits at infinity. And when a limit at infinity is a finite value, this is an indication that either the function becomes that value or is getting closer to that value like a horizontal asymptote. Okay, let's move on to the next page. Now, a function is continuous at a certain input if the two-sided limit exists and equals the value of the output. So looking back on our last page, we are looking for where the two-sided limit and the output have the same value. of these 4 x coordinates that we explored, that only occurred when x was 7. The limit and the output had the same value. So in our graph, we say that the function is continuous here at x equals 7. Of course, 7 is not the only location where this function is continuous. When looking at the graph of a function, focus on a point on a curve. Can you draw through that point without the need for lifting your pencil? If the answer is yes, then we say the function is continuous there. Now, a function has a jump discontinuity at a certain input if both one-sided limits exist but are different. So looking back at our previous slide, we wanted the two one-sided limits to both be finite but be different. So here they were the same. Here one was infinity, so not finite, and here they're both the same. But here was a case where the two one-sided limits were different. As you got closer to 0 in this case, the graph approached one height and then immediately picked up again from a different height as you continued past 0, as if the outputs jumped instantaneously from 3 down to 2 and then continued. So we had a jump in the graph. Now a function has a removable discontinuity at a certain input if the two-sided limit exists but is not the same as the value of the output. So looking back at our table here, we wanted the two-sided limit to exist but be different from the output. So here the two-sided limit did not exist, so we don't look there. Here the two-sided limit did not exist. Here the two-sided limit was 1, but it equaled the output value, which is also 1. But here we had a two-sided limit that existed. It was 4, but it did not equal the value of the output. Visually, we had a situation where the graph was approaching from both sides a certain height where that hollow dot is, but the actual point itself has been relocated or removed to a new location, or perhaps removed entirely. A removable discontinuity is a discontinuity where if you took this point and relocated it to right here, you would create a continuous graph. So the graph would be continuous, but for the fact that a single point has been either relocated or just removed entirely. Now, a function has an infinite discontinuity at a certain input if either one-sided limit is infinite. So in our cases up here, both limits were finite. Both one-sided limits, again, are finite. Over here, both one-sided limits are finite. But here, one of the one-sided limits is infinite in size. So we say that this function has an infinite discontinuity at x equals 3. Consider the image below of the function f. This is the same image that we were just looking at before. Identify all x values where the function is discontinuous and classify each discontinuity. Imagine drawing this graph with your pencil, and at any point in time where you have to lift your pencil, like I do right now, in order to make this point, then I have to lift my pencil again to pick up where I left off and continue. Then I have to lift my pencil here at y equals 3 and then pick up at y equals 2 and continue to graph. Then I would have to lift my pencil again to jump down here to -2 and continue to make the graph. And then from here on, I would never need to remove the pencil again. So I had to lift my pencil at 3 different x values. So at x equals -3, there is a discontinuity in the graph, and this is a removable discontinuity. So we say f has a removable discontinuity at x equals -3. It's as if a single point was removed from an otherwise continuous function. In this case, it's simply relocated down to this height. If the solid point did not exist anywhere, we would still say that f has a removable discontinuity at x equals -3. At x equals 0, we had to lift our pencil, and we say f has a jump discontinuity at x equals 0. This is a jump because the left-sided limit was 3, but the right-sided limit was 2, which are both finite but not the same. And then finally, there's only one more x-coordinate where there's a discontinuity, and that's here at x equals 3. And because one of the one-sided limits was infinity, we had a vertical asymptote on the left side. Then we get to say that f has an infinite discontinuity at x equals +3. These are the only 3 x-coordinates in this image where the function is discontinuous, which suggests that for every other x-coordinate, the function is continuous. So we would say f is continuous for any x in, this is a symbol that stands for in, and I'm going to use interval notation. So any x-coordinate from -infinity up until the first discontinuity at -3. In other words, at every x-coordinate in this portion of the graph, the function is continuous. The function is also continuous for this portion of the graph. That portion I could draw without lifting my pencil. So we could do a u, which is a union sign, which stands for the word or, an interval from -3 up to 0. The function is also continuous for this portion of the graph, which can be drawn without lifting your pencil. So do another union from 0 to 3, and then for this portion of the graph, the function is also continuous, and this is from 3 up to infinity. Okay, let's go to the next page. Fill in any missing values in the collection of statements below. Then draw a function that satisfies these statements. Assume the function is continuous unless the statements suggest otherwise. Classify any discontinuities. Right, this first column of information all deals with x coordinate 4. So I'll put a vertical line at x equals 4 in our image. Then negative 1 is significant, then 2, then negative 5. So let's put 3 more vertical lines in here. I'm going to focus on these bits of information first. So f of 4 equals 0 means that we have a point at 4, 0. F of negative 1 is negative 4, so we have a point right there. F of 2 is negative 1, giving us the point 2 comma negative 1. And f of negative 5 does not exist. So there should be no point on this vertical line. Okay, let's focus on this limit. X approaches 4 from the left. The limit is 3. So this graph needs to be approaching 4 comma 3 from the left. This statement says that as we approach 4 from the right, we need to approach a height of negative 2. So 4 comma negative 2 needs to be a hollow point, and we need to approach that from the right. And it doesn't really matter how I approach it. I can approach it this way, this way, this way, this way. Just need to draw something that depicts the outputs approaching negative 2 from the right side of 4. Notice the two one-sided limits are both finite, they both exist, but they're not the same. So we know that the two-sided limit, which is missing information, but it cannot exist. Now let's focus on negative 1. Notice the two-sided limit is given as negative 4. If the two-sided limit is negative 4, that means both one-sided limits, which are currently missing, both have to be negative 4. Notice that's also the value of the output. When the two-sided limit and the output are the same, the function will be continuous here. So whatever the function is doing, we need to go through that point in a continuous fashion. And there's lots of ways you can draw that. You could draw something like this, something like this, like this, like this. Just pick one. And now we have, as x approaches 2 from the left, we need the outputs to approach negative infinity. That means we have a asymptotic behavior on the left side of x equals 2. Now for this information, as x approaches 2 from the right, the function approaches negative 3. So we have a hollow point at 2 comma negative 3, and we need to be approaching that point from the right. Something like this, or this, or this. There's lots of options. Now because the one-sided limits are not the same thing, the two-sided limit does not exist. Now let's focus on negative 5. Once again, the two-sided limit does exist and is 0. That means the two one-sided limits both have to be 0. There's going to be a hollow point at negative 5, 0. And because the one-sided limits are both 0, we need the graph to approach this hollow point from both sides. It could be something like this, it could be like that, or like that. It really doesn't matter. Now over here we have limits at infinity. As x approaches negative infinity of this function, we approach positive infinity as the outputs. That means as we go left forever, the graph needs to go up forever without bound. So we need to have the graph doing something like this off to the left. And now as x approaches positive infinity, the outputs approach 3. So we need a right-sided horizontal asymptote at height 3. And the graph needs to follow this asymptote. We have some options here. You could follow the asymptote from above. You could follow the asymptote from below. You can sort of oscillate around it, getting closer to it. Or you can even make the graph simply become the asymptote. You got to pick one of these. Now we're going to draw the rest of the function. We do need to assume the function is continuous unless the statements suggest otherwise. So now it's a matter of connecting my bits of the function in continuous fashion. So I want to connect these 2 points in some continuous way. If you want, you can adjust what you've already drawn. So maybe do something like this. Or you could have left this in place and done something like this. It doesn't matter. Now I want to connect this end to this end. Now I want to connect this to that. Now I want to connect here to there. This time I will adjust things slightly. And then finally I want to connect this and this in a continuous fashion. Here's a graph of a function that satisfies all of these conditions. We've drawn a function that's continuous unless the information suggests otherwise. And now we want to classify any of the discontinuities that were forced upon us. We have a discontinuity for this x value, we have a discontinuity at this x value, and we have a discontinuity at this x value. For every other x value, the function is continuous. At negative 5, we have a removable discontinuity because the two-sided limit exists but is not the same thing as the actual output. In fact, the output doesn't exist at all. At 2, we have a discontinuity, and because one of the one-sided limits is infinite in size, negative infinity in this case, we call this an infinite discontinuity at x equals 2. And our final discontinuity occurred at x equals 4. At this value, the one-sided limits existed but were not equal. So this is a jump discontinuity at x equals 4. All right, this concludes part 1 of our 3-part series on limits.